So I am in this really cool program called Desmos. It's free, so feel free to use it yourself if you'd like to. You can't use it on tests, but you can certainly use it to help you with homework. So we learned a library function for x squared, y equals x squared, and recall that it was the graph of this parabola right here. So what we're going to explore in this section is what happens when I add or subtract things from this function or from any of our library functions. So you can kind of make a prediction. Let's say I take x squared and I add 2 to it. What is that going to do to this graph? Well, let's take a look. So notice that adding 2 shifted that graph upwards 2 places. All right, so let's summarize that. So I'm going to put that on a document for you so you can, if you're taking notes, take those down. If we add a number c to any function f of x, it shifts the function's graph vertically in the direction of c. All right, so in this case, we could think of c was a 2, and we added 2 to x squared, and it shifted it up 2 places. So by the same token, if I go back to Desmos and I put a -2, we can expect that it's going to shift it down, and notice that it did. All right, so we add something to any library function, and I want you to notice that it works for any library function. So x cubed, we got that as one of our library, and notice it has its little, I don't know what you would call this, but sort of where it changes its direction here is right here at 0, 0. So let's notice if I add 2, it shifts it up. So it's now changing its direction at 2 places higher. Or of course, if I did a -2, it would move it down. All right, so it works for any function that we use. Okay, now, let's go back to x squared, though, for a minute. And let's take this library function, and let's do a different sort of change. Now, a moment ago, I added 2 out to the side. Let's suppose that inside of this operation of the square, I decide that I'm going to add a 2. Notice. This is a little bit different, maybe different than what you would have predicted. You might have predicted that by adding 2 inside of the square, it moved right 2, but I want you to notice that it did the opposite of that. It moved it left 2. All right, so this is very important. Let's sum this idea up. If we add a number c to the inside of the operation of any function, f of x, it shifts the function's graph horizontally in the opposite, direction of c. Okay, so horizontal shift if it's inside of the operation. Okay, so let's just go back and see that that is true for anything that we choose. So, for example, let's use the square root function. I'm not sure how to do square root in Desmos. Let's see. No, maybe not. Okay, so the square root's the 1/2 power, so I'll just do it as, let's put x minus 2 raised to the 1/2. And of course, you notice that what did x minus 2 do? Notice that x minus 2 shifted our square root graph 2 places to the right. Now, normally, we would write that as a square root rather than a 1/2 power. They mean the same thing. I put that just merely because I didn't know how to put that square root into Desmos. And of course, you can do the same thing when if you decide you want to try to use Desmos. If you've got a graphing calculator, though, you can use the square root button on your calculator and graph it just as easily. All right, so we've got 2 rules so far. If we add 2 or add any number to the side of a function, it shifts it vertically. If we add or subtract inside of whatever the operation of the function is, it shifts it horizontally in the opposite direction of our number. Okay, so now let's look at a different sort of choice. And for this, I'm going to go to, and I think Desmos will allow me to just do, yeah. So there's the absolute value function. That was one of our library functions. Let's take that absolute value function and let's see what happens when we put a negative inside of it. Or not inside of it, but in front of it. So I'm going to put a negative in front of it and it flips it down. So notice that putting a negative in front of one of our functions flips it across the y-axis. We can think of it as a mirror image across the y-axis. All right, so let's sum that up. If we add, or I should say if we multiply by a -1 in front of a function f of x, it reflects it across the across the x-axis. Okay. All right. So I'm going to use a little bit different function for this one, mainly because you won't see a difference if I use absolute value of x. But let's use the x cubed graph. We know what that looks like. That is, again, one of our library functions. And let's put a minus sign in front, or in the inside of the operation. In other words, the x cubed is operating on that minus sign. The cube part is. Notice it flipped it over. All right, it flipped this thing over. So I could, if I needed to, I think I can add another line here. And we can see what the original graph looked like. See, the blue is the original graph. And this is our negative x to the third power. Notice it flipped it across the y-axis. So if we multiply by a negative inside of the operation of any function, so in this case it was the cube part was applying to our negative, it reflects it across the y-axis. Now, you can see why I didn't give you the absolute value, because if we do the absolute value, let's notice just the absolute value function, I'll put it first. And then if I do the negative inside of the absolute value, notice it looks exactly the same. Okay, and the reason for that is because, of course, if we reflect this across the y-axis, it lands upon itself, and so we get the same function again. Okay, now let's stick with the absolute value, because it's a good one for us to do this with, and let's see what happens if we multiply the front of the absolute value function by a number. So I'm going to multiply by 3. Notice that it made it skinnier. It pulled it toward the y-axis. And we refer to this as it stretches it. Okay, you can think of it kind of like rubber bands. It stretches upwards. All right. Now, I want you to notice something, though. On the original absolute value, for example, right here, and not quite perfectly on things, but okay, so there's 1, 1. Let's look at what happened to our x value of 1 and our y value of 1. So 1, 1, if I go straight up, and it's not perfect, trying to get right on it. I am just kind of, there we go. Notice that the y value changed by 3 times what it was before. And of course, that's what we were multiplying by, was 3. If we go to this point right here, 2, 2, not perfect, but it should be 2, 2. I'm not exactly on it. There we go, 2, 2. Well, to 6 is what the new one should be. And so if we go up here, let's notice the y value, and it's not, again, perfect, trying to get perfectly on it, multiplied by 3. All right, so when we stretch this, we stretch it by a factor of 3 when we multiply by 3. If we multiplied by 4, our y values would get multiplied by 4, and so on. All right, so let's summarize this. If we multiply the front of any function f of x by a number c that is greater than 1, it gets stretched, moves closer to the y-axis. Or you can think of it as get skinnier. All previous y values get multiplied by c. Okay, so let's note what happens if, you notice I said that c had to be a number greater than 1. What happens if c is not a number greater than 1? What if it's a fraction? Well, let's go back to our lovely absolute value. And let's, instead of multiplying by 3, let's multiply it by a third, by a fraction. Oops. Okay. Well, notice what happened. This orangish one here is our original absolute value. And when we multiplied by a fraction, it got wider. It got what we call compressed. Think of a trash compactor compressing downward, pushing that thing toward the x-axis instead. All right. And just like before, the 0.11, for example, notice the y value. If we go down here, and I'm not perfectly on it, the y value is now 1/3 times 1, or a third. And 0.333 is just the decimal version of a third. Okay, so same thing is happening, except that it's getting compressed, or it's getting closer to the x-axis if we have a fraction out front. So let's summarize that. So if we multiply the front of any function f of x by a number c that is a fraction, it gets compressed, moves closer to the x-axis. We can think of it, it gets fatter. And all previous y values get multiplied by c again. All right. Now, I'm going to do a bigger example here in a minute, but I'm going to go to a new video because this one, I'm almost out of my 15 minutes that I'm allowed in the program.